folks. Hope you all are having a great Sunday. I am in the workshop and I'm going to be making some videos of a prototype that Chris Young and I have been playing around with. Give you guys a little bit more of a clue. So this is what we're going to be assembling today, and this is a combination of an idea Chris had many years ago, Chris Young from Indianapolis, and a conversation he and I had about how we would do it, how we would solve the same problem today. Years ago, Chris made a device using a Arduino Yun that basically made a very smart wireless gateway for infrared work. So he uses it in his home. If you watch the Chris Young home tour video on YouTube, and I'll put a link here at some point to it, he shows that he can actually change the channel in another room from a web page, and he does that by having a little device on a Arduino Yun. A Yun is a combination Linux device and Arduino in one board. They're kind of expensive and they're kind of outdated, so we thought maybe we could do something using newer tech, and this is what we came up with. And so what this is a Raspberry Pi Zero, which looks just like this. This is a Raspberry Pi Zero W, so it actually is the wireless version of the Raspberry Pi. You can get them for 10 or 15 bucks, and they're dirt cheap. You stick them on your wireless network, and they look like any other PC. And you can plug them into HDMI and have a monitor on them. They've got a USB port, things like that. We could also use this device we're talking about with the standard Raspberry Pi. This is a Raspberry Pi 3 Plus. I'm going to test it on this one. I actually find it easier to test with the full-size HDMI and stuff. But the idea here is, instead of using a Arduino Yun, could we just make a Raspberry Pi Hat, or the small version, which is called a FAT, P-H-A-T, which is the small version of a Raspberry Pi Hat. So we made one. All right. So this has two very distinct parts here. First, the header up here is just so this is just a Raspberry Pi header. It's the 40-pin header that connects it to the Raspberry Pi. On the left, you'll see this is actually a QT Py. So this is a board by Adafruit that basically has a SAMD21 microcontroller and some pins in a very specific layout. It has a I2C port right here, which is called a Stemma QT port, and then it's just got the pins pulled out for this. So it's fairly straightforward, but it is dirt cheap. This entire board here is $6, and it's got, I don't know, 10 pins that you can access, of which I think 8 have analog inputs, and you've got I2C and SPI and things like that. What we're going to use this for is that this board has the timing necessary, the accurate timing necessary to do effective PWM, pulse width modulation, which is needed to send out infrared signals effectively. The Raspberry Pi itself does not have accurate enough timing to do this well. So the idea here initially was just, let's get the ability to have the Raspberry Pi control a microcontroller which does the timing for infrared. The side benefits of this are actually kind of cool. This also, because we took the pins of the actual QT Py and made them available here and here, it also is a way to add analog input and analog output to your Raspberry Pi just by using these pins right here. In order to communicate between this microcontroller and the Raspberry Pi, here we're actually going through 2 pins on the in this header, the RX and TX pins, the UART pins, to send signals back and forth. So that you're telling this one what you want to do. For example, you could say send this code, and it would send the code out, or you could say read pin 6, and it would read pin 6 and give you back the value. So this is a component that it doesn't do anything AT-wise specifically, but it's a really, really powerful tool to have in your toolbox. So let's get to actually making one of these. I think what I'm gonna
Here is the bare board for the project that we're making. It's available open source from a variety of vendors. We'll have links for you to show you where you can purchase it. Here Bill is putting a small drop of solder in the upper right corner of the location where the QT Py is going to go. Now he places the board over the position and melts the solder, tacking it in place temporarily. Notice he got a little bit crooked, so he's reheating the solder, aligning the board properly, and make sure everything looks right. Now that we have it tacked in place, go back and solder each of the pads. Put the tip of the soldering iron in the notch and then fill up the hole with solder. Turn it around, do the other side. Of course, we've got this sped up for you. Here's a closer view. Here are a couple more views of the completed work, just making sure everything looks good. Next, we're going to attach this 40-pin female header to the back side of the board. Now, even though we're doing it now, you might want to wait and do it later, and I'll show you why we shouldn't have done this in this order. We're going to start by soldering temporarily one of the corner pins on the header. Now you pick up the board and make sure that it's flush. You can see there's a tiny gap. Bill is now going to reheat that solder and push on the board and make sure that the header is firmly seated. Now do the same thing at the other end. Pick one of the corner pins, pick it up, reheat it while pressing firmly, and that will make sure that the header is firm against the board. We're going to redo that top one more time. Now that we're certain that everything is securely in place, we can go back and solder all 40 pins, 2 rows of 20. Turn the board around, do the other ones. Now when you get down here close to where the QT Py board has been soldered in place, you want to be careful not to touch that board with your soldering iron. So Bill's going to turn the board around and get it from the other side, just so that we don't damage that QT Py by accidentally hitting it with a soldering iron. Go back and retouch a couple of the pins that might not be fully soldered. Make sure everything looks really good. Now we're going to put in the through-hole components. We have 3 transistors, a resistor, 2 infrared LEDs, and 2 IR receiver chips. Here we're putting in one of the 2 PNP. Note later we will be using an NPN transistor, and they look identical. So make sure that these are PNP, and then the third one is NPN. Bill inserts the transistor into the board and then bends the leads on the back. Here Bill is going to solder one of the pins on the transistor just to get it in place. Then he's going to reach underneath and put some pressure on that transistor and reheat that pin and push upwards on it to make sure it's really seated right. And then we do the same thing on the other transistor. Solder one pin, push up on it, and reheat it. And then we're going to solder the rest of the pins. Notice that as Bill is soldering in his transistors, he gets really close to bumping into that female header. That's why we recommended you do it differently than we did, so you don't accidentally damage the header while soldering in the through-hole components. Now we solder in the single NPN transistor, push it through, bend the leads, and solder it. If you look carefully at the black plastic header, you can see that we accidentally bumped it with a soldering iron. Fortunately, it did not damage it so much that we needed to replace it. That's why I said earlier you might want to wait to put that header in until you've finished the two-hole components. Now we solder in the infrared receivers. The TSMP58000 goes in the slot marked Learn. The TSOP38438 goes in the spot marked Receive. Make sure that you have them oriented with the lens facing outward as shown on the silk screen on the board. Once you have them in place, turn the board over and solder in all the components just like you did with the transistors. Make sure that you push up on the component and reheat that first wire to make sure that you've got everything seated properly, and just solder it up, and when you're done, clip off the leads. Now we add a 1K ohm resistor. There's no polarity on that, so you can put either end in either hole. The holes are a little bit closely spaced, so you won't be able to get it to lay flat against the board. Solder it in and clip the leads. Now we're going to insert the infrared LEDs. The short wire is the cathode, and it goes towards the flat side illustrated on the onboard silkscreen. The long wire is the anode, and it goes next to it. As we insert the LED, we're not going to put it all the way through, like the other components. We're going to leave the leads a little bit long and bend it over 90 degrees so that it hangs out the front of the circuit board. That gives you some flexibility to bend those LEDs at whatever angle that you want to. The blue tinted LED is a narrow angle 20-degree LED, and the clear one is a wide angle 40-degree LED. It doesn't matter which one goes in which spot. Solder all of the leads and clip them off, just like all of the other components. And that completes the basic assembly of the board. We now turn things back over to Bill as he explains some of the options that are on the back of the board.
All right, so the only thing I don't think I did a very good job of showing were the solder jumpers. So I thought I'd make a video for this walking through them. So the first set of solder jumpers are over here. So this is solder jumpers 1 and 2, and these actually bypass the 33 ohm resistors on this side. So you'll notice we don't actually have 33 ohm resistors here or there because we don't need them. They're there if you want them to protect your LEDs and drive less current through it. But by default, these jumpers are soldered closed. They're normally closed jumpers. And if you want those resistors to do any good, you actually have to cut these two and then put resistors in, and you can put them in on either side. It doesn't matter. The others are over here. So there's a set of solder jumpers over here as well. And so you'll notice that that here there's the TX-RX jumper, which is the transmit on one side to the receive on the other. And here's the RX-TX version on the other side. So by default, the UART is connected. So you'll see that this is normally closed solder jumper, and this is a normally closed solder jumper. So if you don't want the UART connected, you actually have to cut those to disconnect them. And then here you have the SCK, MISO, and MOSI. This is the master out, slave in, master in, slave out, and the clock for the SPI interface. So by default, those are not connected to the Raspberry Pi's SPI interface. And over here is the SDA and SCL. This is the I2C interface. And by default, those are not connected either. So if you want the I2C interface, you have to put a dab of solder right here and here. And if you want the SPI interface, you need to put a dab of solder here, here, and there. And you'll also have to pick one of these pins to be your chip select. What I would actually recommend is that you use one of these two if you're using SPI. Just pick one of them and use that as your chip select as well. But I think that's everything. The only other things we didn't talk about in the video were these extra pins that we left visible. So we have all of the pins of the QT Py are pulled out next to them. I didn't label them because they're kind of labeled right here on the pins. They're directly connected. Then we have 2 5-volt, 2 3-volt regulated, and 4 ground in this power grid right here. And then over here we brought out the bottom row of the Raspberry Pi over here on the right. So there are 8 pins of the Raspberry Pi. A couple of these happen to be ground just because of what they were. I could have gone further here, except there's no point because these 2 pins were useless. I think one was 5 volts and one was ground, or one was 3 volts and one was ground, or something like that. Or maybe, I forget what it was. But these 2 weren't very useful. I think that's about it. I think that shows close-ups